Now what we will do is compare our discussion under fluid mechanics and the present discussion under momentum transport. Let us do that. Let us first discuss what we have discussed in fluid mechanics. Tau ix fluid mechanics subscript was given by mu dou Vx by dou y. To be more specific, there is a positive sign because we have now negative sign. So, let us be more specific. Tau ix fluid mechanics is mu dou Vx by dou y, and suppose if we say tau ix is positive, what does it mean? Force along positive x axis on a positive y plane, that is what is shown here. You have a positive y plane and force along positive x axis. That is why for this case, because tau x is negative for this case, on a positive phase, on a positive y phase, we have shown the force along negative x axis. Okay. Now what is that we have discussed now? We have discussed tau ix momentum transport as minus mu dou Vx by dou y. So far throughout the course, throughout fluid mechanics, we have discussed tau ix as mu dou Vx by dou y. Now when we came to momentum transport, because of our sign convention, we are relating tau ix to dou Vx by dou y as minus mu dou Vx by dou y. Now if you say tau ix momentum transport is positive, what does it mean? As we have discussed in the previous slide, it says that flux of molecular x momentum transported in positive y direction. That is what we have, flux of x momentum transported in the positive y direction. So in one case we related tau ix as mu dou Vx by dou y. The second case we have related tau ix momentum transport as minus mu dou Vx by dou y. Okay. Also like to emphasize, which we will discuss in the next slide also, here I say force along positive x axis on a positive y plane. Here what do I say? Flux or flow of something flowing, flux of molecular x momentum transport in positive y direction. Okay. This we will discuss next slide as well. But now, so fluid mechanics represents tau ix as force, of course force per unit area, and in momentum transport we interpret tau ix as flux of molecular x momentum. Okay. That is a basic difference in the viewpoint itself. Both are tau ix only. In fluid mechanics it is a mechanical viewpoint or mechanics viewpoint. So we interpret tau ix as force, of course per unit area. Now how do we interpret? We interpret as flux of molecular x momentum. Okay. Now let us compare the dimensions of the viscous stress and the molecular momentum flux. Okay. Now stress is force per area, force is m L t minus 2, area is L squared. So the dimensions are m L minus 1 t minus 2. Now if you see the dimensions for molecular momentum flux, we have seen that moment is a flux, it is that quantity per unit area per time. We have discussed volumetric flux, mass flux, now we are discussing momentum flux, molecular momentum flux. Okay. And remember when we defined the tau ix in the first instance, we said x momentum is transported in the y direction. This rate of transport of x momentum per unit area is the momentum flux. Okay. So for momentum it is m L t minus 1, okay, this mass into velocity, and then you have area and then time. So once again get the same dimensions as m L minus 1 t minus 2. Certainly they have the same dimensions, physical interpretation is different. Okay. Okay. So let us compare these two viewpoints. Look at the title, viscous stress viewpoint and a molecular momentum flux viewpoint, two viewpoints of the same quantity tau ix. Let us see. So left hand side we have the viscous stress viewpoint which have been following so long throughout our fluid mechanics. When we came to transfer phenomena, when we are discussing now momentum transport, the way in which a viewing tau x is changed, it is molecular momentum flux viewpoint. Now look at the first word. Here we say it acts as viscous stress, because we view tau x as a force, we say it is acting as a viscous stress. Okay. What is the word we should use here? Flows. Okay. Flows has molecular momentum flux. Look at the difference in interpretation. One we interpret as a force and one we interpret as a molecular momentum. One acts, one flows. Okay. Okay. And for a positive tau x, it is a force acting along the positive x axis on a positive y plane, that is what is shown here. What is a positive tau x mean here? It is flux of molecular x momentum transported in positive y direction. Okay. And in terms of regions, exerted by fluid in region of greater y on fluid in region of lesser y. Here what happens? Flows from region of lesser y to region of greater y. In this case, the fluid mechanics case, proportional to velocity gradient and now proportional to negative velocity gradient. So tau x Fm, now this subscript becomes very clear. Why did we introduce that? Is equal to mu dou Vx by dou y, but now tau x momentum transport is equal to minus mu dou Vx by dou y. This two viewpoints also can be explained from a molecular viewpoint. Now for the molecular momentum flux, what we said was we have molecules at a higher velocity, okay, and then when they go to a layer above them, they carry with them higher x momentum and hence transport x momentum to the layer above them. Okay. Now other way of looking at it is the molecules here at a higher velocity, when they reach here they have to be decelerated because that layer is at a lower velocity. Molecules here are at a lower velocity and when they come here they need to get accelerated. So when you have deceleration and acceleration, you should have an associated force. So it is like on you have a layer of fluid and molecules from lower layer to upper layer, when they reach they need to be decelerated, and molecules from the upper layer to the lower layer they should get accelerated. And so it is like a layer on one side, and then of course this deceleration acceleration have their own forces. So it is like a layer and two equal and opposite forces acting on this layer, and which we call as the shear force. If you divide the area you get the shear stress, and that is the viewpoint which helps us to view this molecular motion as a viscous stress. The first viewpoint is the molecular momentum flux. So one way we say that x momentum is transported from one layer to the other layer. Other way is as if you have a layer, because of acceleration deceleration associated forces, you have two forces of equal magnitude acting in opposite direction, which is a shear force divided by area, you get shear stress. Okay. So that is two interpretation of the same phenomenon. Okay. Both these can be related through the Newton's second law of motion at this level, at the molecular level. So Newton's law, you have rate of change of momentum and then right hand side forces, let us say divide each by area. So left hand side is something similar to the molecular momentum flux, right hand side is force per area, which is our viscous stress viewpoint. Okay. Of course more formal derivations are possible, we are not discussing that. Okay. Now one case we have plus, one case we have minus. How do you reconcile both of them? That is the slide about. reconcile fluid mechanics with momentum transport. Fluid mechanics is positive sign, momentum transport is negative sign, but can we reconcile both of them? We can do that. Let us see how do we do that. Okay. Tau x fluid mechanics is mu dou v x by dou y. What is the sign convention for stress which I have been using so far? A positive value represents force along positive x axis on a positive y plane, that is what is shown here. We have come across this several times. Now, what is the sign convention for strain rate? Because this is a one dimensional Newton's law of viscosity which relates stress to strain rate. Now, so let us see what is the sign convention for strain rate, which I have already discussed. For normal strain, elongation is positive. So, for fluids, for normal strain rate, rate of elongation is positive, okay. And for shear strain rate, shear strain is positive when the angle between the two line segments decreases. So, here if the rate of decrease in angle from 9 degrees is positive, then it represents positive strain rate. Okay. So, we adopted one sign convention for stress and then another sign convention for strain rate. Now, tau x momentum transport was given by minus mu dou v x by dou y. How do we introduce the negative sign here? That is a question you have to answer. How do we do that? As we have discussed now, one sign convention for stress, another sign convention for strain rate. Suppose if you change both the sign conventions, nothing will happen here. You change this sign convention, this expression will not change. So, what do? We keep one sign convention same and change only one of the sign conventions. So, we change the sign convention for stress. Okay, I will repeat again. This relationship is based on two sign conventions, one for stress, one for strain rate. We need to introduce a negative sign there. So, we will change one of the sign conventions, namely for stress. So, now in fluid mechanics, why are we doing that? So that we get the same expression as we have obtained for momentum transport. So that the expression in fluid mechanics and the expression momentum transport both will look alike. Okay. So what do we do in fluid mechanics? Change sign convention of stress only, so that tau x fluid mechanics new. Now look at becoming more and more subscripts are there. I think so many subscripts are there. You have tau x and Fm the new, I think very clear. So far we have done tau x, because we are discussing fluid mechanics and momentum transport, we introduce Fm and then momentum transport, but within Fm we have an old sign convention and a new sign convention, that is why it is new. Okay. So nomenclature is very clear, and then now what happens? Minus nu dou v x by dou y. In this case, in the new sign convention, what do you mean by a positive tau x? What does it mean? Positive value represents force acting along positive x axis on a negative y plane, and that is what is shown here. What is that? This is a negative y plane and the force is shown along a positive x axis. So this is the fluid mechanics new sign convention, this is the fluid mechanics old sign convention. I will repeat again, we will keep positive force easy to discuss. So positive force acts on a positive y phase, here positive force acts on a negative y phase, that is the difference, because we have changed the sign convention. Okay. So once again quickly summarize this slide, we are trying to reconcile fluid mechanics and momentum transport. What do I mean by that? The expressions which we have discussed for tau x for fluid mechanics and momentum transport differ by a negative sign. We want to introduce that negative sign in fluid mechanics, and that is we have done that by changing the sign convention for stress. In the old sign convention, positive force acts on a positive y plane, the new sign convention positive force acts on a negative y plane. Okay. Just to understand this two different viewpoints, Let us have very simple small numerical example from this book Brodke and Hershey. Some concepts are explained really nicely in this book, of course a very old book, but physical explanations are good in this book. Okay. Two parallel plates are 10 centimeter apart, the top plate is stationary, the fluid between the plates is water which has a viscosity of 0.001 Pascal second. Calculate the force per unit area necessary to maintain the bottom plate in motion at a velocity of 30 centimeters per second. Calculate the molecular momentum flux at the bottom plate. Okay. Till this it is a typical fluid mechanics problem, because now we are going to compare both the viewpoints. An additional question is added: calculate the molecular momentum flux at the bottom plate. Okay. So, let us use the new sign convention. Tau I x fluid mechanics nu is minus mu dou V x by dou y. Let us write in terms of differences. So, minus mu delta V x by delta y, the viscosity is 0.001 and the velocity difference is at the top plate the velocity is 0, at the bottom plate the velocity is 0.3 meters per second, and so if you substitute you get plus 0.003 Newton per meter squared, and of course it is a constant across the plates, it does not depend on along the y axis. Okay. So, shear force per unit area required to maintain motion of bottom plate is equal to 0.003 Newton per meter squared. Okay. That is very simple as well. Now, what is the shear force per unit area exerted by the fluid on the top plate? Once again 0.003, that is also along the positive axis. Okay. So, let us try to interpret this in the new sign convention, that is the idea of this question as well. Positive sign, we have got a positive value, what does it indicate? Okay. According to the new sign convention, please keep that in mind, and the new sign convention is shown here. Okay. Why is it new sign convention? Negative phase, positive force, positive phase, negative force, that is why it is new sign convention. Now, let us say this, imagine the stress element here, and this positive force indicates that the force exerted by the plate on the fluid is towards the positive x axis, correct. Force exerted by the bottom plate on the fluid is along the positive x direction, that is understandable. Now, just imagine the stress element here, look at this force, how do you interpret that? Force exerted by the plate on the fluid is towards the negative x axis. So, force exerted by the fluid on the plate is towards the positive x axis. So, very simple, all these are known to us. What extra we are doing here is interpret based on the new sign convention, that is all we are doing. So, let us read this: force exerted by the fluid on the top plate is along the positive x direction. Once again, I want to emphasize, all these are forces acting on the fluid right from beginning. Whenever you say viscous stresses or even in solids stress, it is all acting on the solid or acting on the fluid. So, all these are forces acting on the fluid. So, bottom plate force on the fluid is along positive x axis, here force acting on the fluid is along the negative axis. Okay. Now, we will calculate the momentum flux. This is what we have done in the previous slide based on the new sign convention for fluid mechanics. Okay. And now, for momentum transport, tau x is equal to tau x momentum transport is equal to same expression. Why is it same? Because this expression has been written based on new sign convention, that is why both the expressions are same. tau ix fluid mechanics knew, tau ix momentum transport have the same expression. Okay, so same steps will give us 0.003 Newton per meter squared. Once again it is constant across the plates. Numerically they are same. How are we going to interpret this? That is different. How are we going to interpret? It is a positive value. What does it mean? Molecular momentum flux at the bottom plate is equal to plus 0.003. What is the correct interpretation? If you have a positive sign, indicates that molecular x momentum flux transport in the positive y direction along direction of decrease in velocity, very complete description. Molecular x momentum transport into the positive y direction. Why is it along positive y direction? Because the flux is positive and along direction of decrease in velocity. Okay. So, now in the first case we interpreted this as shear stress or shear force acting per unit area. In the second case we are interpreting that as molecular x momentum flux transported in y direction. In the first case it was shear force acting in x direction on a y plane. In this case it is x momentum flux transported in the y direction. See, the direction of momentum is x, direction of transport is y. Like in the other case, direction of force is along the x axis, the plane on which it acts is y. Here similarly the direction of momentum is x momentum, the direction through which along which it flows is y axis. So, in that way they are analogous. Okay. We will see more about this later as well. Okay. So, let us summarize what we have discussed so far. Tau can be interpreted as viscous stress, the fluid mechanics viewpoint, molecular momentum flux, the momentum transport viewpoint. Both the expressions for tau can be reconciled if the sign convention for stress is suitably changed. That is what we have discussed so far. Okay. We took our usual planar cover flow, took the other case where the bottom plate is moving, gave a molecular interpretation to tau, and then but that resulted in a negative sign. So, we want to reconcile that with the expression which I have discussed so far in fluid mechanics. That could be done by changing the sign convention for stress.